everybody. My name is Dr. Marina Milner-Bolotin, and I would like to show you something that you can do at home, and it will cost you only a couple of dollars. If you go to a dollar store, you can buy a set of those, the ones that I bought. They're called crystal pearls. They have different names, and this set is something like this. That's the bag that you can see inside. Those tiny pearls, the interesting thing about them, that when you put them in water, they can grow. So you put them in water, and in about a couple of hours, from very small ones, and I'm going to take one to show you the size of one. It's about a couple of millimeters in diameter. I hope you can see how small they are. So if you put them in water, and I just have a little bit of colorful that's why they're pink, they will grow to become much bigger ones, as you can see here. The interesting thing about them is that they're made out of a very long molecules, and those molecules have the ability to attract water, and they can grow up to I would say 90% in size from how they were at the very beginning. We can even do the math and calculate the ratio volumes of the small one, and now they're falling. You can see they're very bouncy. You can see how they bounce. Here I want to show you two, a small one and a big one, and you can see the difference in size. But what I want to do now, I want to show to you that in a way, when you're holding them, you're just holding a sphere practically made out of water. And something really cool happened. So first of all, when we discussed optics with you, we discussed that if you have a lens, and a lens is, we can have spherical lenses, we can have parabolic lenses. The lens has an ability to make something look bigger, to create images that are bigger or smaller, inverted, upside down, or upright. So to show you that it's a lens, what you can do, you can take this sphere, you can put it above something which is written and play with it and see how it can increase. When you look at it, it is just like a magnifying glass. Now to do that, you're doing it, but I hope, do you notice that that is letter S, but this letter S, I hope that you can see what's going on here. The interesting thing also, that depending how far you put it, the images can also be upside down images. So that's really cool if you give it to a child and allow them to play with it. By the way, they're made for flowers because they can absorb so much water. If you put them in a pot and you go away, they will release the water slowly. Or imagine if you have a plant and you don't have time to water it, you just put it in with a lot of water and leave it for a couple of weeks, it will not die. But what I want to show you is something really cool. I have a glass of water here, and it looks absolutely transparent. It's just water, nothing else. Here you see the bubbles that are also, or the balls, you can, pearls, whatever you call them, also made out of water. I want to ask you, what is going to happen if I pour this water on top of that? It's going to be water inside water. What will I see if I do that? While you're thinking about it, I'm going to do it. If I were to teach it, I would have asked the students to predict what will happen. And after they think and they have different answers, what will they see? Will they see the bubbles? Will the bubbles look bigger, smaller? I'm going to do it. And what also I'm going to do, I'm going to take some of the bubbles out for a different experiment. Or you know what, I can leave them. That's okay. I'm going to pour the water slowly. Let's try it. I'm pouring the water, and now I'm going to show you the glass with the bubbles. You saw the bubbles were there, and with water. If you look very carefully, you might see the edges of the bubbles. But it mostly looks as if it is absolutely transparent. So it's really cool. And the reason you don't see the bubbles is because you don't see water in water. They have exactly the same index of refraction. The water outside and the water that the bubble is made of have exactly the same index of refraction. So the light passes through it without refracting and nothing interesting happens, and it looks absolutely transparent. Now the cool thing is, what will happen if now I'm going to pour the water back? I'm pouring the water back. So you can see the bubbles are there. What if instead of water, I'm going to pour canola oil? I have canola oil here, and I'm going to pour a little bit of water at the beginning. A little bit, so let's pour a little bit of water. I hope you can see the water at the bottom. Now I'm going to pour canola oil. So once again, after we say cheers, let's predict what is going to happen if I pour this oil. Will the bubbles remain invisible? Will we be able to see them or not? Now to answer this question, think if the index of refraction of oil is exactly the same as the index of refraction of water. I also want you to think about another topic of buoyancy when we discussed with you earlier that how density is important too for decision about what's going to be on top, what's going to be at the bottom. The density of oil is less than the density of water, which tells me that the layer of oil is going to be on top of the layer of water. So let's see what's going to happen to the bubbles. Going to pour it slowly. I hope you've made your predictions, so let's look. Now, when you do all those experiments, make sure you have your napkin. You don't want to pour the oil on the table. And I hope it is absolutely clear to you that the bubbles are clearly visible where the oil is and are almost invisible where the water is. That's a really nice demonstration showing the importance of the difference of indices of refraction in order to see something. Thank you.